is team number 8, E-Fire.
Hello everyone, welcome. We're Team E-Fire. My name's Derek Kenyon.
I'm Nate Mishner.
I'm John Markeo.
I'm Casey Pelkowski.
I'm Jing Hall.
So what is E-Fire? E-Fire is a proof of concept for an electric field measurement instrument that uses passive radioactive hot electrons for use in small spacecraft such as nanosatellites.
So measuring electric fields in near-Earth space is vital information for various space physics studies. Electron drift is the phenomenon that explains the small displacement of an electron's final position after gyrating along a magnetic field. E-Fire's concept looks to utilize electron drift to measure surrounding electric fields. Our customers are Professors Ronald Nepper, Brian Walsh, and Theodore Fritz. Here is an illustration of electron drift. If you imagine a magnetic field coming out of the page in a perpendicular electric field, the electron travels in a circular path and comes to the triangles you see, which is a diode detector which detects the high energy electrons.
So here's a current picture of our test setup. First, I'm going to mention the test pulsar. That is simulating the radiation source, this collimator, the diode array, and the biasing board. Next, we have the analog PCB, and that houses the ASIC MyRock2, which is the mainframe of our entire project. We can see different outputs and different control signals from that chip on the oscilloscope, as well as just other processes that we can put through the system. And we have our digital PCB that houses the BeagleBone Black. That is the interface board between our analog board and our other systems. And finally, we have our Miniboard Max server that lets us display our HTML page.
So kind of converting what Casey said to text, we have 3 printed circuit boards that we designed. One was a biasing network, which Casey's holding. It biases our diode detectors. Then we've got an analog board housing MyRock2 that stands for multi-channel integrated readout circuit designed by Professor Nepper's previous PhD student, Hex, Dr. Zhang He. And then we have a level shifting digital board from plus minus 1.65 logic to 0 to 3.3 for a microprocessor. The BeagleBone Black, which has a lot of input pins that we need, and then that interfaces through UART to a Miniboard Max, which is running a Python WebSocket server, so we can connect our GUI from any laptop connected to the internet.
So one of my lead roles on this project was to design a biasing board for the diodes on the diode detector. I was looking to bias 12 diodes, so there's a network of 12 biasing networks. This board connects directly to the male pins on the back of the diode detector that you see on the bottom left, and via a female socket on the bottom of the board. And then also the board has 2 screw holes to align with the screw holes on the diode detector. My other jobs in this project was to develop a data processing program and bias the diodes on the detector. The data processing program takes in two bytes from the BeagleBone, which include the channel triggered and the energy level of the high energy particle that strikes the diode. Then it records the strike number and the time of the strike and compiles that into a CSV file. Biasing the diodes allowed us to find a bias voltage that was nowhere near the reverse breakdown region of the diodes, but was still within the depletion region, which provided a small yet constant leakage current.
My main responsibility was to design the analog board, which houses the MyRock chip. The MyRock chip 2 has 19 channels of charge-sensitive amplifier, and it has 3 8-bit digital ADCs to generate the digital signals. We also add 2 sets of linear regulators to regulate the supply voltage. We also have 15 test points to monitor the operation of the MyRock 2, and 4 switches to control the operation of the MyRock 2.
So my main responsibility for this project was to design the digital interface board. The interface board interfaces the analog PCB that Neil designed and the BeagleBone Black, as well as the BeagleBone Black and the Miniboard Max. The main functionality of my board is just level shifting. It level shifts from the plus minus 1.6 logic supplied from the analog board to the 3.3 logic on the microprocessor. My other responsibility was to fabricate the collimator that we were going to use with the diode array. The purpose of this collimator is to direct the high energy particles exactly where we want them, so we can simulate a calculation for the E field. So one of the design features that was made for this part was it attaches directly to the diode array.
My responsibility in the entirety of this project was to develop a driver to control MyRock 2. This driver waited for a trigger input from MyRock 2 and then sent various control signals such as start signals, clock, and a couple reset signals, as well as taking the digital input from MyRock 2. This program was written in assembly and C, and that connected to the Miniboard Max via UART to proceed onto the data processing program and the server that we'll talk about in a bit. My other responsibility was to integrate everything together to make sure that everything from the bottom level assembly all the way to the user interface proceeds correctly and that all the data comes up as it should be.
And I had a couple responsibilities. My first one was to design a GUI, which just ended up being an HTML web page with a JavaScript library, you'll see in a minute, to create a bar chart to display our output. My other main responsibility was system integration and test. So we had some old PCBs that worked with MyRock 2. They had a lot of problems, so part of our job was to discover those problems and see how we could fix them. That involved a lot of noise debugging, which we can talk to you later about at our demo session. I also looked at testing amplifier linearity, ADC linearity, and dynamic range. So some of those properties of MyRock 2 we could use.
So coming up, we have a video of the whole system in use. We will see in oscilloscope with some of the control signals to MyRock 2, including the clock and the serial output. And on the other side, we have the user interface, and you'll be able to see the data start coming in and start to be plotted on the graph.
So you'll notice the pulser's at one energy setting, and in a minute John's going to change it, and we'll get a distribution of output pulses further to the right along our graph, representing a higher ADC output. And there you go. So our customer installation basically was what you just saw. We demonstrated our system functionality end-to-end from the pulsar out to our software output. We came up with this distribution, and you can look at full width half max noise from that. So each of those tall spikes corresponds to one nominal energy input, and then you get kind of a noise envelope around it representing different sources of noise in the system, so we can do some analysis with that. And our customers were pleased.
All in all, Project EFIRE met most of our customers' requirements that we received initially last year. And along the way, we learned a lot about debugging noise mitigation, integrating software and hardware together in a full system, and really debugging and seeing how each aspect affects each other. We'd like to thank our customer, Professor Nepper, Fritz and Walsh, George Bunder for populating our boards, Terry McManus for fixing our diode array, Zhang He for developing the MyRock 2, and the senior design core staff and anyone else who helped us along this way. Thank you very much. We'll take questions now.
Could you describe, I have two questions. One, the collimator. Did you
design it based on like a schematic that you had, or did you model it in any way?
So the design originated from the vacuum chamber we were initially going to put the boards in. So initially at the beginning of the year, we thought we were going to use this rectangular sort of vacuum, but we found out that it didn't work. So the design is based around us being able to manually set up where we want which diode we want to hit, and then we can know through the system what diode you want to hit.
So the idea was that the collimator would slide up and down
Yeah.
to cover a different diode, because there was a post we could adjust. Yeah.
And then you mentioned noise mitigation. Can you explain some of the sources of noise and what kind of increased that distribution?
So I'll let Nate go into this a little bit, but I'll introduce it. So there was actually noise coming from photonics itself. There was an environmental noise that we were seeing, and we took a lot of different steps to shield that, from shielding SMA connectors to using different connectors to actually probe the points and see the waveforms on the oscilloscope.
Yeah, so we had a lot of trouble with actually noise in the ground in this building, and because I mean, even if you get a 5 millivolt peak-to-peak ringing, it would come out in hundreds of millivolts after our amplifiers. Yeah, and so if you think about that distribution, though, there's going to be, I mean, those are sources of noise. That extra ringing is going to adjust up and down the height of the pulse going in, and you can see that in our setup. But there's going to be some fluctuation there.
Could you explain the vacuum safe electronics design and where that's integrated in your system?
So originally this setup, the collimator diode array and interface board, or biasing board, along with the analog board, was meant to be in the vacuum chamber, and to take steps to make sure we didn't outgas anything. I did extensive research on what materials did and did not outgas, and made sure everything we were including on those boards was vacuum safe.
We had to think about power dissipation as well.
Right, so the vacuum was meant to simulate near-Earth orbit, basically. So we wanted to make sure that everything we had could work in those conditions.
You guys mentioned you had some assembly code in there. Can you talk a little bit about how that came into play and what was the need for it?
So the driver relies on 2 real-time subprocessors of the TI-AM3358 chip. So those 2 subprocessors basically just run on, you load assembly code directly onto them, and they'll just operate based on that code. So the C program, its main purpose was to initialize those processors, load the assembly code onto them, and then execute them. And the program would then receive interrupts from the processors and just pull whatever important information from them from just direct memory access.
Eugene, so you had a minnow board. Can you explain why you had to use a minnow board instead of just GigaBone to use internet connection as well?
So we submitted this entire project to the Intel Cornell Cup, where they require an Intel chip to be used. If it was possible, we would have used the minnow board in full replacement of the BeagleBone, but the BeagleBone had the required number of GPIO pins that the minnow board only had something like 20, and we required almost 40. So the minnow board was used as a requirement for that competition, but the BeagleBone is also required just for the number of pins we need.